Good morning. I'm kind of quickly running through and logging some attendance here just so we're keeping track of everyone in this challenging time when it's kind of easy to skip class and for people to kind of get lost in the shuffle of everything. Okay. Okay. So what we're going to do today is really introduce our new topic that'll occupy most of the rest of the term. All right. But what I want to start with is, well, first kind of showing a couple things on the Canvas page. Okay. So one thing to watch out for is these lectures are always being recorded. So there's a YouTube links page. This is the review session that we had before the exam. What'll also be up here, I don't know if it's up here now, but also the lecture notes that I'll be kind of walking us through will be posted up here. So you can go back and look at anything that we saw or that you saw or heard during these lectures. But before we really get to the main topic, or where we really start, I want to kind of jump to the end and see where we're trying to go with all this, because we're making a very big shift in the kind of topics we're talking about and the ideas that we're introducing. So a question that can be asked is, e to the x is this exponential function. How do you approximate it? On the one hand, this isn't the most relevant question because, well, e to the x, you want to compute e to the x at some point, just put it in your calculator. Well, questions that can be asked are, what if you only had like a 4-function calculator? Or what is your calculator doing? And so we can imagine wanting to approximate other functions that maybe our calculators aren't specifically built for, using simpler functions. So some more accessible methods of guessing values of e to the x. And one way we can do this, as you might see here, is we'll approximate it with polynomials. So as a bad approximation, this horizontal line y equals 1 is not very good, but it does cross here. Okay, so it's correct at one point. An approximation that we have seen before is 1 plus x. If you dust off your Calc 1 skills and you find the slope of, or you find the equation of the tangent line of e of x at x equals 0, it is x plus 1. The slope at the slope at 0 is x plus 1. Sorry, the slope of e to the x at 0 is 1, and the equation of the tangent line is x plus 1. And if we look at what is happening, or we remember really what the tangent line did for us, if we zoom in close to 0, this green tangent line is very close to the red curve e to the x when we're really close to 0. And that's what it means to be, really what it means to be tangent. You just touch the graph at 0, but close to that point where you touch the graph, you were a very good approximation. So this was a Calc 1 idea. You can approximate functions with the tangent line. But a question which maybe didn't come up, but if you think of it, might make a lot of sense is, what if you use a more complicated function than a line? How good of an approximation can you get? So in particular, if we look at this next function, a parabola, this purple parabola is much closer to the red line. As we get further away from 0, it's not very good, but if we look close to 0, the red line is e to the x, the green line is the tangent line, so the green line is pretty good close to x equals 0, but it gets worse as you get further away. The parabola, on the other hand, sticks close to e to the x pretty well. As you get further away, it gets worse, but close to 0, it's even better than the tangent line. Oops. And then we have these other functions which have the same beginning, but we keep adding on more terms. So this cubic, this black cubic line, especially out here, the black line is even closer to the red line than our purple parabola was. And on this side, the red line is almost being covered up by the black cubic line. So this cubic is an even better approximation to e to the x than the parabola was. And if we go one step further, we graph this fourth degree polynomial. It sticks with e to the x even longer. Okay. So getting just those, we have our e to the x function, and then we have our fourth degree polynomial, and especially going out this way, they stick really close together. They're less good out the back, but for positive x's, they're staying really close together. So there are a lot of interesting questions that arise in seeing this. One thing is, does this pattern continue? We have this list of polynomials. Well, I guess maybe question 0 is, what is the pattern? Where am I coming up with these? The second question is, so supposing that we figured out what the pattern is, does this phenomena keep happening? If we kept lengthening these polynomials, would we keep getting polynomials that are really close to e to the x? And to understand this, we need to back things up and think about some simpler situations before we get to these functions being close, this list of functions getting closer and closer to some fixed function e to the x. That phrasing right there, a list of functions getting closer and closer to some fixed function as you go further and further out the list, that sounds a lot like some kind of limit phrasing. You go further and further down the list, you get closer and closer. That sounds a lot like some kind of limit at infinity that we talked about. So that's where what we've seen before can kind of tie in, but this is a different situation. So what we'll want to do is we're going to start talking about what are called sequences, which are just lists of numbers. And we'll want to see what happens if you have a list of numbers. does it happen as you go further and further out the list? Do you get closer and closer to some number? What we'll also do is think about particular lists of numbers, particular sequences that look like you're adding more and more things up. So in this case right here, it's not just some ever-changing list. So we start with 1, then we add on a new term x, a new term x squared, a new term x cubed over 6, a new term x to the 4th over 24. If we look at lists of this particular type where your list is you have something but you add on it something else, and then you add on a new something to that and a new something onto the end of that, how can we tell what happens with those kinds of lists? So where we're going is we're going to be talking about sequences of functions, in particular sequences of polynomials where we're adding more and more terms as we go down the list, and how those seem to get closer and closer to some function which is definitely not a polynomial. So that's where we're headed, but we need to spend some time in the more basic setting before we work our way up to what really is the end goal of this kind of long-term project, this section of the course. So these notes will be posted on Canvas afterwards, so you can take a look at them. One thing I'll say is these are notes from a previous version of the course. It's still the same material that we want to talk about, but rather than having to take pictures of lecture notes on my phone, these were scanned in with a nice copier, so it looks much nicer. So I'd say ignore the chapter numbers. There's some dates in here. Things will be posted so it corresponds to the dates that we actually see them, and that's what the file name will be. So I said that what we want to look at are lists of numbers and kind of what happens to that list as you go further and further out. So the word we'll actually be using is we're going to be talking about sequences. So a sequence is just an infinite ordered list of numbers. And in general, this looks like we have some first thing in our sequence, in our list, a second thing in our sequence, a third thing in our sequence, a fourth thing, and so on. So anytime you have a list of, or an ordered list of numbers, that's going to be a sequence. And the sequences that we're looking at will always be infinite. Some other ways of writing this are, we might have these curly brackets around them, really indicating that we're thinking of this as an object. A sequence is the whole list. Some more compact forms are, we'll be getting formulas for what each term of the sequence looks like, and we'll write that as the sequence of an starting from n equals 1 up to infinity, which is to say starting n equals 1 and then keep going and don't stop. So different sequences will start at different places. There's always some ordering, but for some reasons, you might say the first term corresponds to, an index other than 1. So when we're talking about sequences, the things in the sequence are called the terms of the sequence. Every term has an index telling you where it lives in the sequence. So the last term that we left off, A5, that's a term of the sequence, and the 5 here is the index telling you that it's the 5th term of the sequence. Or it won't always be the 5th term, but it'll tell you it corresponds to the number 5. Where there can be a slight difference is if you start counting at 0 or 1, or maybe your first term has an index 4. Then your sequence would be a 4, a 5, a 6, a 7, and so on. So the index tells you where it falls on the list, not always necessarily its position in the list. Or in terms of first, second, third, but it tells you a 5, the next one is a 6, and then a 7, and so on. So how we'll be dealing with sequences most of the time is that we want a formula in terms of n. So we want to know for index 5, what is the 5th term of the sequence? For index 10, what is the 10th? What is the term corresponding to index 10? And if we can get that formula, which will have a variable n in it, we're going to call that the general term of the sequence. So the general term says every term of the sequence looks like this for different choices of n. And if you pick a particular n, then you get the corresponding term for that index. So as some examples of actually doing this, we have some lists of numbers, and we have some sequences here, and we can say what is the general term of each of these sequences. So what you're trying to do is come up with a formula that says every term of the sequence looks like this for different choices of n. So if we take our first term as just 1, 2, 3, 4, 5, we want a formula which is producing these numbers as we start picking different n's. A general term is just an. The first term corresponds to n equals 1, the second term corresponds to n equals 2, and how you find the term is you take the index, and that is the number. So if we wanted to know what term corresponds to index 10, well, this says a sub 10 would just be the number 10. Where we see something actually happening is if we look at this sequence 1, a half, a third, a fourth, and so on. So in these sequences, there's some pattern that is happening, and we want to identify the pattern and say, every term of the sequence has this form for different inputs of n. And in this case, especially if you write this first number 1 as 1 divided by 1, what you see is that the top is just fixed. The top is always 1, but the denominator keeps growing by 1 every time. And so we want to see how can we have a formula that says when we put in 1 or some number, we get 1, the next number gives us a half, the next number gives us a third, and 1 over n works as a general term. So 1 over n starting at n equals 1 is the form of every term in our sequence. And if we wanted to know more of the terms, you could say, well, what is the term with index 7? That would be a7, and we would put that 7 in for n and get 1/7. A sequence where it is much less clear what is happening, or where the pattern is really pretty apparent, but finding a formula for it is not quite as clear. So here's a sequence 1, -1, 1, -1, and then it keeps going. 1, -1, bouncing back and forth between them forever. So in this case, describing the pattern is clear. 1s and -1s flipping forever. But how can we write that in a formula? And one way of doing that is in this way. Let the nth term be -1 raised to the n minus 1. with the idea being, if you take -1 and you start raising it to whole number powers, well, -1 to the first power is -1. -1 squared is +1. -1 cubed is -1 again. -1 to the fourth is 1 again. And that is starting to get us this alternating pattern. So we can see that if we take -1 and start raising it to higher and higher powers, that we get this alternating. One thing that you want to watch out for is that you want to make sure that you actually get the sequence that starts with 1. So for instance, if you took just -1 to the n and started counting at n equals 1, then your first term would be -1 to the first power, which is -1, which isn't what we have here. So this thing is starting at n. Sorry, I haven't done this before. So that's pretty messed up. But this is starting at n greater than or equal to 1. So for n equals 1, the exponent is 0. That gives you 1. For n equals 2, that gives you 1. That gives you -1. And so that is what gives us this pattern. So what can be important to keep in mind is not just the formula, but making sure that you pick the right starting point to actually give you the sequence there. Another option is you could have -1 to the n for n greater than or equal to 0. So that's another way of writing, of giving a general term that produces this sequence. In this case, if you start counting at 0, then -1 to the 0 is 1, -1 to the 1 is -1, -1 squared is 1, and so you still get the alternating, but it's a slightly different looking formula, but it produces the same sequence because you're starting in a slightly different point. Okay. A sequence which will be showing up a lot, but until we really see the formula, it's not clear what it is the sequence 1, 2, 6, 24, 120. And on its own, it's not clear what's happening. Going from 1 to 2, you might think, well, it's increasing by 1, but then from 2 to 6, that doesn't work. You could also think from 1 to 2, maybe it's doubling, but that doesn't work. 2 to 6 isn't doubling. So how we can see what's really happening is taking these numbers and factoring them and looking at what is the pattern in the way that they're factored. And how we can write this list is 1 is just 1, 2 we'll write in kind of a silly way 1 times 2, but 6 we can write as 1 times 2 times 3, 24 is 1 times 2 times 3 times 4, 120 is multiplying the numbers 1 through 5, and that looks like the pattern. So where these numbers are coming from is that we're multiplying every time we're putting on the next number and multiplying that. Numbers, or this sequence of numbers, is what's called n factorial. This exclamation point is a kind of function which says, take this number n and multiply all the whole numbers from 1 up to n. And so n factorial, that is the general term of this sequence, starting with 1 factorial and 2 factorial and 3 factorial. And we know that those are the right terms because actually computing 3 factorial, for instance, is 1 times 2 times 3, which is 6. So this factorial is a sequence-specific kind of function. So I mentioned that what we're going to want to do is, given some sequences, what happens as you go further and further out in the sequence. That is a kind of limit type question. And so we've been talking about limits before, so that will inform what we're doing now, but also there are going to be some new sequence specific things that we'll have to watch out for. Okay. Another way that sequences are given is they can be given recursively. So in these 4 cases here, these general terms are giving the sequence explicitly, meaning you want to know what the 70th term of your sequence is, just put 70 in for n, compute whatever number that is, and that gives it to you right away. But there are some sequences which are more naturally presented, not explicitly, but what's called recursively. Maybe the most famous example is what's called the Fibonacci sequence. So the way that this sequence is presented is we're told the first term of our sequence is 1, the second term of our sequence is also 1, and from that point on, if you want to know a term of the sequence, the nth term, take the term right before it and the term 2 before it and add those together. So this way of understanding this sequence, if you wanted to know, say, the 10th term, there's not a formula that you can just plug 10 into and get whatever number out. How you would find the 10th term is you would need to take the 9th term and the 8th term and add those things together. But then you have to know the 9th and 8th term. And if you want the 9th term, you really have to take the 8th term and the 7th term and add those things together. So how these recursive sequences work is, if you start from the bottom, you can start building up further and further terms in this sequence. And you can if you have some term you want to know, you can always build up to it, but you always have to start at the bottom or from terms that you know. So for instance, if we want, so we have A1 and A2, if we want A3, what this formula says is that let n equal 3 and substitute it into this recursion formula here. So if n equals 3, then that says A3 equals A sub 3 minus 1, which is A2, plus A sub 3 minus 2, which is A1. So this is saying you want to know the third term, take the one right before it, which is A2, the one 2 before it, and A1, and add those things together. And these two are terms that we were given. So this is something that we can actually compute. A1 is 1, A2 is 1, adding them together we get 2. And this is how we have to keep going. If we want, say, A4, then what we have to do is take A3 and A2 and add those two things together. Now, A2 was one we were given, and A3 is one that we computed. So we have figured out what both of these are beforehand, and now we can use that to figure out what A4 is. A2 we were told was 1, and A3 we figured out was 2. So a 4 is 2 plus 1, which is now 3. And this pattern continues. So we've so far figured out that our sequence goes 1, 1, 2, 3. How we keep finding them is, say, add the last two together, and that gives you the next one. So this is A5. How we find that is add a 4 and a 3 together, and 2 plus 3 is 5. And keep repeating this. 3 plus 5 gives us the next term 8. 5 plus 8 gives us the next term 13. 8 plus 13 would give us the term that I didn't write, which is 21, and then we can keep going. So this is one way where we can still figure out every term of this sequence, but we can't just jump right in the middle like we could with the explicit general terms. We have to kind of start from the bottom and work our way up. But we're told how we keep working our way up so we can identify any term of the sequence. We just have to really know all of the terms before that. Okay. Questions about this sequence stuff so far? Okay. So most of the sequences we're looking at will be given by these general terms, but recursive sequences do appear in different places, so it's good to at least encounter them now. So the big question about sequences is what happens as you go further and further out? And this is a kind of limit question, which we have spent enough time talking about limits that we have some ideas about how it's going to work. So we're talking about sequences, and we want to talk about the limit of a sequence. So given a sequence an, a sequence will have a limit L if the terms in the sequence can be made arbitrarily close to L by taking n sufficiently large. So this terminology appears in Calc 1, and the idea is that you can make a to the n as close to L as you want by going far enough out in the list. Or said another way, as you go further and further out on the list, you get closer and closer and closer to L. And if this happens, if the sequence an has limit L, then we'll write this as the limit as n goes to infinity of a sub n equals L. So talking about limits of the sequence, it's very analogous to when we were talking about limits at infinity of functions. And for sequences, that's the only kind of limit that makes sense. Since a sequence is a list where you can keep going further and further out, everything is really a limit at infinity. It doesn't make sense to talk about the limit at a point. So the kind of limit machinery that we really need to think about and is most relevant to now think about sequences is all the times that we've been talking about limits at infinity. Some other terminology is that if a limit exists, we'll say that the sequence converges, and if the limit doesn't exist, then we'll say that the sequence diverges. Okay. So this is like when we were talking about improper integrals, really, was where this terminology appeared. There's this distinction converging and diverging. And if you know that a sequence converges, you can further ask, what does it converge to? And that answer, what does a sequence converge to? That's the limit that we're talking about here. So let's try a couple examples out. Yeah. So first up, let's take the sequence which has general term n starting at 2, and then all of these sequences start somewhere and then go to infinity. Okay. So this sequence, if we were to write it out, the first input we get is 2, so that's 2, but then so our first thing we put in is 2, and then we do 3, 4, 5, and so on. Those are the inputs that we're putting in. And since this formula is just n, the terms of the sequence are just those numbers again. So the terms of the sequence are 2 as our first one, and then 3, 4, 5, and so on. So we want to ask, what happens to this list of numbers? And this list of numbers keeps growing, 2, 3, 5, 6, 7, and so on. And so this sequence never actually gets close to any fixed number. So this sequence is going to diverge. And like we did when we were talking about limits at infinity, we can write that the limit as n goes to infinity of the sequence n is infinity. So we can write that down, but we'll say that the sequence diverges because it's not getting close to a number. Another way that a sequence can diverge is that maybe it doesn't go to infinity or minus infinity, but maybe it just doesn't settle down. So if we look at one of these alternating sequences that we had seen an example of before, so we'll take -1 to the n, starting at n equals 0, and then going from there. So n equals 0 gets us 1, n equals 1, we get -1, n equals 2 gives us 1, n equals 3 gives us -1, so we're bouncing back and forth between 1 and -1 again. This sequence diverges, not because it goes off to infinity, but because it just keeps bouncing back and forth and never actually settles down to anything. Okay. So this example would be like, let me pull this up. Don't need these. So in that case, the alternating part would be if you think about sine of x. So thinking of this as a function, it's a function of x, not a sequence, but the limit as x goes to infinity of sine x, that limit doesn't exist because sine just keeps oscillating back and forth. Sine never settles down, and so that was a case where the limit at infinity didn't exist because we were just bouncing around. And so that's the kind of behavior that's happening in this case. So we're just bouncing around, so the sequence diverges. Okay. But with that example in mind, we do have to be more careful because some sequence behavior might be a little bit different than what you would expect in terms of functions. So for example, let's look at cosine of 2 pi of n. Now, if we graph this function, so cosine of 2 pi, we use x in here. Okay. The 2 pi kind of compresses it, but we still have this oscillation. So if we look at this function and look at its limit as x goes to infinity, that limit doesn't exist. So that's something that we've seen before. The function is oscillating, so the limit as x goes to infinity doesn't exist. But if we think about this as a sequence where we're only using whole number inputs for n, starting at n equals 1, we can think about what does the sequence actually look like? Well, if we put in n equals 1, cosine of 2 pi is 1. If we put in 2, that's cosine of 4 pi, which is also 1. N equals 3 is cosine of 6 pi, which is also 1. So as a function of a real variable, where we're allowed to put anything in, this function is oscillating. But if we think of this as the general term of a sequence where we're only allowed to put in whole numbers, we keep getting 1. So what's happening here is, if we zoom in, if we put in just these whole numbers, we keep being at the top of these peaks. And so in this case, this sequence is converging to 1 in the way that limits of constant functions were wherever they were. If this sequence is always 1, then it's sitting at 1 the whole time, it's not going anywhere, and so then it's definitely as close to 1 as you'll ever want it to be. So this is a small warning that this function, which looks like it's oscillating, because we're only using whole number inputs, it in fact is 1 the whole time, and so it's sitting at 1 and converging to that constant 1 value that it takes. Okay. What do I want to do? So this one I'll come back to in a second. But if we look at just this sequence, so if we're asking about the limit as n goes to infinity of 1 over n. So this is asking, here's this term, or here's this sequence. What happens to this? And in this case, we can really think of this like we would with, like we really did with functions. Here's this expression. The top is fixed as 1, and the bottom keeps getting bigger and bigger. And so what's happening to those fractions is the fractions keep getting smaller. And that is what we see in this list: 1, a half, a third, a fourth, a fifth, a sixth, and so on. So in this case, this limit is 0, and the sequence converges. Okay. So a lot of the ways that we thought about limits as the input goes to infinity still apply when we're talking about this. We do have to be careful in some new situations. There's some situations which didn't really apply this alternating sequence is something kind of new, but in a lot of ways, we're treating these limits of sequences like we did with functions. If you have a fraction, the top is fixed and the bottom is going to infinity, those fractions are going to 0. So this sequence converges, and it converges to 0. All right, let me. So as one last example of talking about specific sequences converging, we can look at this expression, n factorial over n plus 1 factorial. Now, if we look back at what n factorial looks like, that was one of our sequences. That's this sequence. N factorial on its own goes to infinity. The numbers keep getting bigger and bigger. Yep. So in this case, the top and bottom, they both keep getting bigger and bigger, and that gives us really an infinity over infinity form. So we can't, like we did with just 1 over n, say that what happens is that the top is fixed, the bottom is 0, the whole fraction goes to, the bottom's going to infinity, the whole fraction's going to 0. In this case, the top and bottom are both becoming infinite, so we have to fall back on how do we deal with that. And with factorials in particular, the way that can help you understand factorials inside sequences is to write out what it actually means. So write it in terms of the multiplication that's happening. So n factorial, what that means is start at 1 and keep multiplying the numbers until you get to n. And that's what's happening here. 1, 2, 3, 4, 5, so on up to whatever n is. N plus 1 factorial is telling you to do the same thing, but with a different stopping point. This is saying start at 1 and then go 2, 3, 4, all the way up to n plus 1. So if we write that out, we go 1, 2, 3, 4, and so on, n, but then n plus 1. So these are all the consecutive numbers from 1 to n plus 1 all multiplied together. And if this example, I think in particular, getting used to factorials, if it helps to actually write out what these terms look like, to see that there is this multiplication, and as happens, we get some nice cancellation, that can kind of help make this a little bit more concrete. But in this case, writing it out as multiplication, why that helps is that we see that if you were to compute this, there is just a ton of cancellation. The top is start at 1 and multiply all the numbers up to n. The bottom is start at 1, multiply all the numbers up to n, and then do the next number n plus 1. So in this case, there is a lot of cancellation. The 1s, 2s, 3s, and everything cancels, except the bottom has this extra factor, n plus 1. So after simplifying, we've canceled everything on the top, and we just have this extra factor on the bottom. So what we're really dealing with is 1 over n plus 1. And this, we can either write out what that looks like. So in this case, starting at 1, if we put in 1, we get 2 on the bottom. So we start with a half, but then we keep this pattern going. We get a half, a third, a fourth. And so this is really the sequence that we had just looked at, but we start in a different place. And with sequences, if you start in a different place, you are, but the ends are the same, then you're going to converge to the same number. Converging, it only matters what happens far out. So if we're starting a little later than 1 over n, the example we just talked about, that doesn't affect what happens in the long run. So in this case, either looking at these terms or using the same analysis saying the top is fixed, the bottom keeps growing to infinity, and if that's what's happening in a fraction, the whole fraction is going to 0. So this sequence converges to 0, not because we can look at it right away and tell that's what's happening, but because we can simplify it. And if we look at the limit of this sequence as n goes to infinity, we can tell that that goes to 0. Okay. So where we're going to pick up next time is that the ways that we think about sequences, of limits of sequences, is in most ways the same as limits of functions. There are limit laws, which are really similar to the ones we talked about for functions. And in most cases, or cases where the limit of the function exists, you can think about, or you can use that same thought process to deal with the sequence that you would get. In particular, that means rules like things like L'Hopital's rule and the squeeze theorem still apply. So what we're going to do is these notes are going to be posted, and the lab tomorrow from 12 to 1, I'm going to be talking about more examples of sequences, in particular, seeing how the kind of limits at infinity that we've done before are really similar and kind of thought about in the same way as these limits of sequences. So tomorrow in the lab, which there won't be anything graded, but I say to get a handle on how these sequences work, you should really come up to see some more examples and get some practice. We're going to talk about how what we know about limits still helps us evaluating limits of this new kind of object sequences rather than functions. Okay. So if you have any questions, I can stick around for a little bit, but if not, I would, then I'll hopefully see you guys tomorrow and then Friday. If you came in a little late, stick around so I can make sure that I got you marked as present. There aren't going to be attendance points, but there, I guess it is important to keep track of who's coming to these so I can make sure that you're not getting lost in the craziness that is moving everything online. So let me see. So I think I got everyone. Let me. So on Friday, I'll be talking a little bit more about sequences, but I'm going to be putting a lot of examples in the lab tomorrow. And the lab tomorrow is going to be recorded, and the notes are going to be posted on Canvas. So if you can't make it, you can see what we talk about. But to kind of make up for a lost week, I'll be trying to talk about sequences largely tomorrow with a little bit more on Friday, and then get into the next topic, which is series. All right, so I can stick around for any more questions, but if not, I'll see you guys tomorrow and Friday.